Hello, chemistry students. Dr. Tullis here. Welcome back to Chapter 12 on solutions, where you will learn about solutes and solvents, electrolytes, non-electrolytes, and what a saturated and unsaturated solution is. Let's get started.
The career focus of this chapter is a dialysis nurse who assists patients with kidney disease who are undergoing dialysis. They monitor patients before, during, and after dialysis, and they must know how dialysis machines function in order to ensure their safe use. The first section in this chapter is about solutions. You'll be able to identify the solute and solvent in a solution and describe the formation of a solution. Most of the gases, liquids, and solids we see around us are mixtures of at least one substance dissolved in another. The air we breathe is a solution that is primarily oxygen and nitrogen gases. Carbon dioxide gas dissolved in water makes carbonated drinks. When we make solutions of coffee or tea, especially tea for me, we use hot water to dissolve substances from coffee beans or tea leaves. The ocean is a solution consisting of many ionic compounds such as sodium chloride dissolved in water. In your medicine cabinet, the antiseptic tincture of iodine is a solution of iodine dissolved in ethanol. Solutions are homogeneous mixtures of two or more substances. Solutions contain a solute, which is usually in smaller quantity, and it's uniformly dispersed in another substance called the solvent, usually present in a greater quantity. Here we have a picture of salt, and salt is the solute because it is the substance that is present in the lesser amount. Here we have water. It looks like we have 400 milliliters of water or so, and so we're pouring the salt into the solvent, the substance where there's a greater amount, and we then have a solution. Solutes are not visible and cannot be separated by filtration, but they can be separated by evaporation, and they can give color to a solution. Here are a bunch of different types of solutes and solvents. When we have gas solutions, like gas in a gas, like air, we have oxygen as the solute and nitrogen gas as the solvent. For liquid solutions, we can have gases in liquids, a liquid in a liquid, and solid in a liquid. Notice that for our solvent, water is a very common solvent. Here we have ethanol, like that iodine example, iodine dissolved in ethanol. But for soda water, we have carbon dioxide dissolved in water. For ammonia, we have ammonia dissolved in water. For vinegar, we have acetic acid in water. For seawater, we have salt dissolved in water. We can also have solid solutions. I know this is a hard one to comprehend sometimes because you're like, a solution, but it's a solid. We can have brass, which is zinc dissolved in copper. So those two mixed together, it's a homogeneous mixture. We can also have steel, which is carbon and iron together. Like I said, water is one of the most common solvents in nature. In the water molecule, an oxygen atom shares electrons with two hydrogen atoms. We know that we have O with H and H. Because oxygen is much more electronegative than hydrogen, the OH bonds are polar. We talked about this. We had electronegativity values for every element on the periodic table, and O is more electronegative. This end is slightly negative, and our hydrogen end is slightly positive. Same with this bond over here. Slightly positive hydrogen end, slightly negative oxygen end. In each polar bond, the oxygen atom has a partial negative charge and the hydrogen atom has a partial positive charge. Because the shape of a water molecule is bent, just like we showed up here, its dipoles do not cancel out. It would cancel out if I had a linear compound like CO2. If I have this linear compound, we know between C and O is a polar bond. But because we have a polar bond pulling this way and pulling this way, they cancel each other out. It's like equal tug of war. Water is polar and is a polar solvent. Attractive forces known as hydrogen bonds occur between molecules where partially positive hydrogen atoms are attracted to partially negative atoms. These three in particular, I remember them as FON, like fondue, fluorine, oxygen, and nitrogen. They're very, very attracted. Hydrogen bonds form between an oxygen atom in one water molecule and the hydrogen atom in another molecule. Notice though that it's not an actual bond. It's kind of confusing. These little dots right here, the dots are showing the bond, but it's not a bond. It's just a very, very strong force of attraction, but it's not a bond. It allows the oxygen in one water molecule to be very attracted to a hydrogen atom in another water molecule, and they want to be very close to one another. That slightly negative is very attracted to that slightly positive, and it wants to hold that water molecule close to itself. Attractive forces occur between solute and solvent particles when the solute and the solvent are similar in polarity. The expression like dissolves like describes the common polarities of the solute and solvent particles needed to form a solution. So because like dissolve like, that means my solute, if it is polar, then the solvent needs to be polar. If the solute is nonpolar, then the solvent needs to be nonpolar. That's the only way that that solution will form. If a solute is polar and the solvent is nonpolar, they won't mix. It won't form that homogeneous mixture. Let's look at these pictures. In each test tube, the lower layer is CH2Cl2, which is more dense. The upper layer is water, which is less dense. So in A, CH2Cl2 is nonpolar and water is polar. The two layers do not mix. One is polar, one is nonpolar. Nope, they do not mix. Let's look at B. We have nonpolar solute, iodine, which is purple, and it's soluble in the nonpolar solvent CH2Cl2. Okay, so these two would mix. Letter C, the ionic solute of nickel nitrate, which is green, is soluble in the polar solvent of water. So if it's soluble, that means it must also be polar. So this nickel nitrate must be polar, and water is polar, so they will mix. Here we go. Solutions will form if my solute is polar and the solvent is polar, good. If the solute is nonpolar and the solvent is nonpolar, good. Solutions will not form if the solute is polar and the solvent is nonpolar. No. If the solute is nonpolar and the solvent is polar, no, they will not form if they don't match. Likes dissolve likes. In water, which is polar, the hydrogen bonds provide strong solvent-solvent attractions. Now let's say that we have NaCl crystals, sodium chloride. We know that NaCl, Na forms a +1 ion, and Cl forms a Cl- ion, and those form an ionic compound. Now an ionic compound is extremely polar, right? It's not in the polar covalent or non-polar covalent category. It's beyond that. Remember, if I took Na's value and Cl's value and I subtracted it, it's going to be way above that 1.8 value that makes it polar, because it's then an ionic compound. So an ionic compound is just an extreme polar compound, which is okay. It's still polar, and it will dissolve in water, which is a polar solvent. And because likes dissolve likes, and it dissolves in water, that Na plus ion is going to be very attracted to the partially negative oxygen atoms, and the Cl minus ions are going to be very attracted to the partially positive hydrogen atoms. So let's look at this solution of NaCl in water. On the surface of an NaCl crystal, we can see that the different attractions to the water molecules. We can see the Na pluses right here are attracted to the O's on water, and the Cl minuses are attracted to the H's on the water. And we can see what happens is that in a solution that's hydrated by water molecules, they surround each ion. So notice I have an Na plus ion, and that positive is going to be surrounded by all those negative oxygens. And the chloride ion, that's minus, is going to be surrounded by all the H pluses. See how the water molecules turn so that the H side of that bent molecule is facing the Cl minus? And when that happens, we can write it like this. We have our NaCl, our solid sodium chloride. And when dissolved in water, we can see the separation of their ions into Na plus in aqueous solution and Cl minus in aqueous solution. Another polar molecule is methanol, and methanol is CH3OH. Now we know that CHHH, these three H's, carbon and hydrogen, if I looked at the electronegativity chart, these three bonds are nonpolar. Carbon and H, one was 2.5 and 2.1, so the difference was 0.4. But when we add this OH group, OH, this right here is a polar bond. And if I have one polar bond in a whole compound, it makes it polar. And because of that, this polar methanol is soluble in water because water is polar and methanol is polar. You can see these red lines that are showing here. These are those hydrogen bonds. Again, not a bond, just an attraction between the slightly negative end of one and the slightly positive of another compound. So if this is this red ball is the oxygen, it's going to be attracted to the hydrogen in another compound. And because the methanol is polar and water is polar, when we mix them together and we have methanol and water, we can see the hydrogen bonding that's also happening between the hydrogen in the water molecule and the oxygen in the methanol. There's a strong force of attraction. And again, the hydrogen of the methanol to the oxygen in the water of another molecule. Some solutions that are nonpolar, like iodine, oil, grease, they do not dissolve in polar water. Again, we know that nonpolar and polar will not mix because likes dissolve likes. There are no attractions between the nonpolar solute particles and the polar solvent. Nonpolar molecules will form a solution with nonpolar solvents. Take a minute to look over the review for section 1.